The 2024 Methods Exam 1. The examiners have actually said it best. Too many students forgot brackets, sloppy working cost marks. Verify, show that, hence. These words have precise meaning. Many ignored them. Transformations, wrong axes, wrong direction, wrong language. So notation, transformations, and instructions. That's where students fell down. Let's go through the solutions today to make sure that you don't make these same mistakes. Exam walkthroughs. Welcome to Exam Walkthroughs with Sophie, where I don't just show you the solutions to the exams, I show you how to think through and break down questions so that you can access the full marks. This year, not only do we have the examiner's assessment guide, they've actually also given us the marking guide, which is going to help us know exactly where the marks lie. So I'll be going through all of that along with the solutions today. While I'm completing this exam, you'll notice I'm going to be using two highlighters. So the pink one is going to be for your key information and the green one for instructions. I would always recommend to highlight through your exam so that you can pick out all the key instructions and information. Also, I'm going to be using 3 colored pens. So the black pen is going to be for my working out, the things that I would actually write on the exam. The blue one is for my thought process so that you can see what I'm thinking through. And finally, the red one is going to be for the examiner's assessment guide and also any remarks that they might have. Let's get into it. The Methods 2024 Exam 1. So question 1 says, let y equal e to the x cos 3x. This is a pretty stock standard question. You're usually going to be faced with a product rule or a quotient rule question for the first one. In this case, because we have two functions being multiplied by each other, we're going to be using the product rule here. In terms of the instruction, the key thing that we need is to be able to find the derivative. Find dy by dx. Again, that's using the product rule. So of course you can do this in your head if you like. For me personally, even though it might take 10-20 seconds longer, I actually prefer to write down all of the separate functions and their derivatives just to make sure that I'm not going to make any mistake. So to start that off, I'm going to write the first function I can see, which is e to the power of x, and the derivative of that, very nicely, is e to the power of x. Then our second function is cos 3x, and the derivative of that, we'll pull out the derivative of the inside, which is 3, and then cos becomes negative sign when we derive it. Now for the product rule, we multiply across. So we'll write dy by dx, and we will write e to the x. Now negative 3 sine 3x, we usually write the value or the number out the front, and then sine 3x plus, and then our second multiplication, ex times cos 3x. So that there is your answer. Now in terms of the examiner report, 82% of students have gotten this question correct. The key thing that they noted is that students lost marks because they wrote y equals instead of dy by dx equals. So it's really important to pay attention to that notation. Also, in terms of the brackets, you don't have to include them, so they still gave the mark as long as it was really obvious that the 3x belonged to the sine and the cos. So that's pretty much it for the first part. Let's move on to the second part, part B. Let f of x equal log e x cubed minus 3x plus 2. And it asks you to find f dash of 3. So again, this is a stock standard question for part B, usually requiring the chain rule. So we've got our instruction here to find f dash of 3. And when there's more than one step, what I like to do is label each of the steps, because in an exam, sometimes when you're under pressure, you kind of get an answer and you move straight on to the next question. Whereas if you label the 2 steps to this, so I need to find the derivative, that's step 1, and then I need to substitute in 3, that's step 2, then I know to check at the end that I've completed each of those steps. Now, the second thing is that the function that we're using is log e x cubed minus 3x plus 2. Of course, you can use your standard chain rule, derivative of the inside multiplied by the derivative of the outside. But log is actually quite easy to do because there's a general function that we can use for its derivative. So what I'm thinking of is log e of g of x is equal to, so when we do our derivative, it'll just be the derivative of the inside on the derivative of the outside. Now, whether you use this rule or just go through your normal chain rule method, you'll get the exact same answer, but this rule is obviously a lot quicker. So let's start off with our step 1. That's going to be f dash of x is equal to, and we'll do the derivative of the inside over the function inside. So that's step 1 done. I go back and check, and now I'm up to my step 2. So step 2 is where I'm going to go ahead and substitute in the value of 3. Of course, again, you can do this in your head. I prefer to just write it out just to release that mental load so there's not too much that I'm trying to do at once. Now for this next step, we're going to go ahead and do just our basic arithmetic. So 3 squared is 9 times 3 is 27, minus 3 is 24. And then 3 cubed is 27, minus 9 is 18, plus 2 is 20. And we should always simplify our fractions. So 24 on 20, 4 will go into both of those numbers, and so your answer will be 6 on 5. So in terms of the examiner's report for this one, we have 54% of students that got this question correct. 30% of students actually didn't get any marks at all, so they couldn't even differentiate it. But then that does mean that there is a number of students who were just not able to substitute in 3, which should be a very simple task, really. So 30% is 0 marks. That's for the differentiating part, which is what I would say is the hard part. Substituting should be easy, but of course it's so easy to make a mistake in it. I think I'm just going to get rid of all of that part. In terms of where the marks were allocated, so the first mark was allocated for finding the derivative, and then the second mark, surprisingly, was allocated for the unsimplified fraction. So as long as you got to the fraction, it doesn't matter if you didn't simplify it, you still got the mark. In saying that though, I always recommend that you do simplify your fractions. Usually they're a little bit more lenient on your earlier questions, and then towards the end, they will be a lot more strict. So don't risk it in saying maybe they might award it, maybe not. Just always simplify your fractions. But in case you forgot, you would have still gotten the mark at that point. All right, that's the end of question 1. And now moving on to question 2. Consider the simultaneous linear equations as written there below, where x and y are part of the real number set and k is a real constant. So determine the value of k for which the system of equations has no real solution. Hopefully this question is something that looks super familiar to you. It's set out exactly as it would be over and over again. That's usually using the same language, and it's the same method that you would use as well. So to break it down, let's highlight our key information. We can see that they are simultaneous linear equations. We know that everything is a real constant. And finally, in terms of our instructions, we're determining the value of k. Note that it says value and not values, so you should only get one answer. And the key part to this is that we want no real solutions. So we want to kind of break that down a little bit. What does no real solution mean? It means that the lines are parallel, and parallel lines have the same gradient, but they do not have the same y-intercept. So that's essentially what we want to do. We want to find the values where the gradients are the same. That would be my first step. And the y-intercepts are not going to be the same. That would be the second step. Now, in terms of completing this question, it really depends on how you've learnt it. There are 3 methods in which you can do this, and the most common method is by rearranging our equations into y equals mx plus c. But you can also do this through using ratios and through matrices. Today I'm going to do it using our gradient intercept method, just because that's probably the most common one that's used across the board. But if you are interested in using any of the other methods, which in my opinion are faster, but they are different, let me know and I'm happy to create a side video to that. So in order to do this, we've already kind of laid out our steps. We want to equate the gradients to find the values where k will be the same, and then we want to figure out specifically which k value will then give you a different y-intercept. To do that, I'm going to get my equations into that y equals mx plus c mode. So I'm going to just label this as equation A and equation B, and I'm going to rearrange this in my head. I will explain the thought process, but of course, if you want to write it out by hand, you are welcome to do so. It's better to take a little bit of extra time and not make a mistake right at the beginning. So we're trying to isolate y for equation A, and because there's a negative, I'm going to actually take this whole term over to this side, and I'm going to take this term over to that side. I'm then going to divide both sides by -2 to get the y by itself. So y will equal, so first of all, the 3kx is already there, and then I'm taking over the k plus 4. So that means the entire term is subtracted, or you put a minus sign in front of each term. So make sure that you're careful with your negatives there. Then of course, as we said, we need to divide both sides by 2. Now for equation B, we're doing something very similar. We're going to take this term over, and then we'll divide both sides by k. So y is equal to, and this term now becomes negative. And there is a minus k, but just thinking ahead, because I'm also going to divide by k, k divided by k will be equal to 1. So I'm just going to go ahead and write 1 straight away. And this term needs to have that k divided through by it. Okay, we've now got equations A and B, and so we're going to go ahead and complete our first step that we labeled, which is to equate the two gradients. So here is my first gradient and here is my second, so I'm going to equate them and then I'm going to solve for K. I'm just going to specifically highlight not the X. Okay, so this is step one now, just to label it very clearly. We're going to equate the two sides. And I will cross multiply to get everything to the top. And as I multiply the 2 over, I'm going to expand at the same time. So expand the negative in, that becomes positive 4, and then times by 2, that becomes 8. I'm going to take everything over to one side, and I will be left with a quadratic. So from this step, now I'm going to go ahead and solve for that quadratic. So what I'm thinking of are two numbers that multiply to give me the product of 3 and 8, which will be negative 24, and two numbers that add to give us 2. In this case, those two numbers will be 6 and 4, and we want the larger number to match the sign of the internal number there. So that would be plus 6 minus 4. So I'll go ahead and split that middle term up. We'll end up with 3k squared plus 6k minus 4k minus 8 equals 0. And then I'm going to factorize by grouping. So that means I'm going to pull the 3k out. I'll be left with k plus 2, and I'll pull out the negative 4. I'll also be left with k plus 2. Now I can factorize this term, k plus 2, and I'll be left with 3k minus 4. And finally, I can solve for k. So the two values, in order to get the gradients to be the same, are k equals negative 2 and k equals 4 on 3. So now my next step is to find, well, which value of this k will give us a y-intercept, a constant value, that is going to result in a different y-intercept. So the way we do that is to substitute in our k values. And as we said, we want our c value to end up different. So here are our c values. And we want these to be different. Very nicely, one of them is already solved, negative 1. So essentially what we're trying to say is which number, when I sub it in, is going to result in this not being negative 1. Sometimes, in fact, most of the time, you'll also have a k value there, so you'll have to solve both of them. But this is very nice for us. All right, so when k is negative 2, if I substitute that into our first equation, I'll just label that as equation A. So negative 2 plus 4 is going to be 2, and there's a negative on the top. Negative 2 divided by 2 will give me negative 1. So what we can see is that when k is negative 2, our constants are going to be equal to the same, so it cannot be negative 2. At this point, you can assume that k equals 4 on 3 will be the correct answer, and if you're running out of time, absolutely just write that down and move on to the next question. But let's go ahead and just check just in case. So k equals 4 on 3. If we go ahead and substitute that in, what we can see is that that is not going to equal to negative 1. So 3 times 4 is 12, plus 4 is 16. And then the 3 and the 2 multiplied will get negative 16 on 6, which very obviously does not equal to 1. So that leaves us with k equals 4 on 3 will give us no real solutions for our simultaneous equations. And just make sure that your answer is highlighted very clearly like that. So in terms of the examiner's report, this question was not very well done considering it was question 2. 37% only were able to get full marks. The marks were assigned as follows. So the first one was to be able to get some sort of relationship between the two gradients like this. The second mark was not only to get to the quadratic, but also to show some sort of an attempt at solving it. So you wouldn't just write the quadratic out, you needed to show that you've actually tried to solve it. Not necessarily that you had to, but just shown that you have tried. And finally, of course, our last mark will be assigned to k equals 4 on 3, which is no real solutions. So that were the key sort of aspects of this question here. Of course, as I said, there are 2 other methods that you can try as well, but it is a very stock standard question. Like this question, or this type of question has this very specific method. It's never going to change. So it's something that I would really encourage you practicing, particularly only because 37% got it right. There might be a chance that it could be on the exam again this year. So please practice this method. Moving on now to question 3. Let g of x equal the following equation, and on the axis below sketch the graph of g of x, labeling all asymptotes with their equations and axis intercepts with their coordinates. So this is a sketching question, things that we should highlight. First of all, always highlight the domain. In this case, it's the maximal domain, but sometimes they'll throw you a random domain and a lot of students will lose marks because of that. And then of course, there's the actual equation itself if you wanted to highlight it or just keep note of it itself. Now, in terms of the instructions, it says on the axis below, sketch the graph, labeling all asymptotes with their equations and axis intercepts with their coordinates. Of course, you should do this regardless, but the fact that they've clearly said it means that there are going to be marks there. And if you don't do it, you're going to lose your marks. Okay, so in terms of this question, this here is a truncus. So what I'm immediately thinking of is the particular shape, and I'm also thinking of its special points, which are asymptotes. This function has moved 3 to the left and 2 down, which means our asymptotes are going to be x is equal to -3 and y is equal to -2. Our other key points that we always need to include are the intercepts. So we'll find our x-intercept and our y-intercept here. So I'll just start off with the x-intercept. You are welcome to write this on the exam, and it's also worth doing it just in case, because sometimes examiners, like if you don't get to the actual sketch, they might be able to award you something for writing down the intercepts. So let's start off with our y-intercept where x is equal to 0. So that'll be y equals 0 plus 3 squared minus 2. That'll be 1 minus 9, 1 on 9 minus 2, and then 9 times 2 is 18, and 1 minus 18 is -17 on 9. So our y-intercept will be 0 and -17 on 9. Next, we'll have our x-intercept. That's when y will equal to 0. So 0 equals 1 on x plus 3 squared minus 2. I'll take the 2 over. And then I'm going to swap these two. So the way we do it is we multiply by x plus 3 squared and divide by 2 at the same time. Then I'll take the square root of both sides. So that'll result in plus minus 1 root 2. And then finally, I'll take the 3 over to the other side. Now I have run out of space, so not that you can do this little trick on your exam, but I'm going to do it here. So that will be x is equal to -3 plus minus 1 on root 2. Those are our two x-intercepts. Okay, we've got all of the information now to go ahead and sketch our graph. Let's start off with our asymptotes. So I'm going to label my asymptotes very clearly. So, and then the other thing is that we need to use our dashed lines. If you use a straight line, then that implies that it's actually part of the graph, but the asymptotes are not part of the graph. So we'll start off by drawing a dashed line down -3 and also a dashed line at -2. And then we will go ahead and label these. So this is x is -3 and y is equal to -2. So those were the two asymptotes that we determined earlier on. Next, I'm going to substitute in my key points. So for my y-intercept, -17 on 9 is just shy of 2. And then for my x-intercepts, -3 plus minus 1 on root 2. Yes, it's true, we won't know what this value is here, 1 on root 2. Hopefully you know that root 2 is approximately 1.14. And then 1 divided by 1.14, because 1 divided by 1 is just 1, and the number is a little bit larger, it's actually going to end up being just slightly under 1. We can kind of approximate it. You can just make up a number if you like. Let's just say it's going to be around 0.8, so something that is just under 1. So -3 plus 0.8 is going to be almost -2. And then -3 minus 0.8 will be just under -4. Now, you don't have to be that precise. And in fact, the examiners, as I'll talk about in the end, even if you kind of gave it over here, they were still okay with that. But this is just a way of being able to think about it. Now, what we might want to do from here, we can go ahead and sketch the graph, but if you want to be super precise, it's actually nice to be able to find one more value if you can. So what I would try to do is usually sub in some other value in my graph that's very clearly on the grid into my function and see if I can find a y value for that so I can put it in there. Now I'm going to go ahead and substitute the values that are just around the asymptote. I also know it's going to work out nicely just by thinking about those numbers. So you can choose anything, but sometimes it's nice if you can choose numbers that will work out well for you. Let's start off with x is equal to -4, 1 minus -4 plus 3 squared. And this is what I mean by it works out nicely. I know that -4 plus 3 is just going to be -1. -1 squared is 1. 1 divided by 1 is 1. So that point is going to be over here. Now, because this graph is symmetrical, I can assume it's going to be there, but let's just check in case. So that'll be x is equal to -2, 1 minus -2 plus 3. That's going to be also 1. So there you go. All right, so now I've got a few points. I can go ahead and draw my graph as best as I can. All right. I think it's pretty good. It can definitely be better, a little bit more symmetrical, but it is definitely hard to sketch a graph. And I think the examiners also understand that. So as long as you've got those key points in there and it's looking as symmetrical as you can, then it should be all good. Okay, so it looks like it's all done. I'm just going to quickly revisit the question to make sure that I've done everything. So it says on the axis below, sketch the graph. Great, we've done that. Labeling all asymptotes, we've done that. And also labeling the axis-intercepts, I have not done that. So very good that I've actually gone back to read over it and make sure that I have written in my axes-intercepts. And for this one, that will be 0. You don't have to label the extra point that you found if you wanted to find that extra point. The main thing is those axes-intercepts. Okay, let's talk about the examiner's report because they have plenty to say about this question. First of all, only 42% of students actually managed to get full marks on this question, but there are lots of fiddly elements to it. So 3 marks, where do they come from? The first mark comes from the shape. That's making sure, of course, that you have that truncus shape, but there's also a couple of things that they highlighted. First of all, a lot of students try to sketch their graph as if they're some sort of artist. We don't want to see that. We want one proper straight line. So there's no multiple lines and no sketching as though it's an artwork. Okay, so just one line. The other thing is when you work with asymptotes, you have to make sure that they always veer towards the asymptote, whereas it's very easy to accidentally do something like that, where it comes closer and veering away. And it's also a very common mistake. So if you do that, you will not get the mark. So make sure your asymptotes always make sure your function always approaches your asymptotes. Next thing, the second mark was assigned to the asymptotes themselves, so drawing them in clearly and also writing in their equations. One thing they noted is that if you drew your asymptotes using solid lines, you did not get the mark, and the reason for that is that solid lines indicate it's part of the graph, whereas the asymptotes are not part of the graph, we're just saying that they exist there. Finally, the last mark belonged to the intercepts. They did note that if you dropped one bracket, so you accidentally forgot to write 1, they still gave you the mark. However, if you did it more than once, then they probably took off the mark at that point. So 42% got that full mark. It is worth noting, though, that 2.1 was the average. So we still had about half the student being able to get at least 2 marks, but it was just that final mark that a lot of students were not able to get. I just realized that that should have been step 3. Okay, so that's part A. Let's move on to part B. Determine the area of the region bounded by the line x equals -2, the x-axis, the y-axis, and the graph y equals g of x. So let's start off by talking about the instructions. So we need to find the area between the line x equals -2, the x-axis, the y-axis, and the graph itself. So whenever I think of the area and a graph, I hope that we're thinking of the integral, so that we're specifically thinking of the definite integral where we've got 2 bounds. And in fact, they've told us what our boundaries are, which are over here. So let's go ahead and try and sketch that part out. So we've got the line x equals -2, the x-axis, the y-axis, and the graph. And so that region that's bound between it is the area that we want to find. So I'm just going to quickly color that in. Try your best to color in inside the lines, unlike me. I don't know how it's going to work. There we go. All right, so that's the part that we're trying to find. Whether or not you want to do that on your exam is up to you. If you do, just make it very clear to the examiners that that's not a part of part A, or you can use pencil and then rub it out later. Okay, so what we're going to do is try to set up a correct integral to start off with. So we have the area is equal to. Now, because the area, that shaded area, is below the x-axis, we actually need to put a negative, or alternatively, you can flip the bounds around, whichever one you prefer. And we're going to integrate it between 0 and -2 of the function. So if I scroll up to look at the function, because I have the power at the bottom, I'm going to take it to the top just to make it a little bit easier for myself. So that'll be x plus 3 to the -2, and then it's -2 over here. And don't forget the dx, as that's an important part of the notation to say that we're integrating with respect to x. Okay, so let's go ahead and integrate that now. So the negative, and then we're going to use, it's kind of like the backwards chain rule, and you can only apply it if it's linear inside the brackets, which in this case it is. So what we'll do is we'll add 1 to the power, and you divide by the new power, and also by whatever the derivative is of the inside. In this case, it's just 1. And then for the constant, we just add an x. Now I'm just going to simplify this just to make it a little bit easier for myself in a moment. So that's going to be negative 1 on x plus 3. So I've just taken it to the bottom and I'm taking the negative out the front, minus 2x and negative 2 is 0. Okay, so we're all set up and ready to go to substitute in our bounds. So I'm going to substitute in the top bound first, which is just 0. So there's a negative on the outside. We'll deal with that later. And so that'll be a negative third minus 2 times 0 is 0. And then minus for the second bound, I'm going to put everything inside the bracket. So that'll be negative 1 on negative 2 plus 3. So negative 2 plus 3 is positive 1, and negative 1 divided by 1 is just negative 1. And then negative 2 times negative 2 is going to be positive 4. Okay, so I've got negative on the outside. We've got the negative third inside the bracket. 4 minus 1 is going to be 3. And then there's a minus on the outside, so that'll be negative 3. So now we've got to work out negative 1/3 minus another 3. So 3 times 3 is 9, and then minus 1 minus another 9 will be negative 10. And then 2 negatives will make a positive. So that's 10 on 3 units squared. So that's how you will integrate this. Make sure that you do get a positive area. And if you don't, then it's because you probably haven't included that negative right from the beginning. In terms of the examiner's report, so first of all, only 27% of students were able to get full marks for this question. It's quite low. Where the marks were distributed, so the first mark was for not only setting up a correct integral, but also to attempt to solve it. So that might be to try to integrate it or substitute the bounds, whatever it might be. And what is also an important part of setting up this integral is this dx. If you did not include the dx, you actually lose a mark for it, because the dx clearly indicates that we are anti-differentiating with respect to x. Now, the other mark, of course, comes from the answer, but the examiners have noted to say that that 10 on 3 has to come from a correct area statement. So it must have dx. So you need to show the working out mark to get to this 10 on 3, and it has to come from a correct area statement. So just be careful in terms of your notation and your methods, but that's how we go ahead and complete a question such as this. Moving on now to question 4, some lovely probability. Let x be a binomial random variable. So starting off with question 4, let x be a binomial random variable where x is the binomial random variable with our n as 4 and our probability as 9 on 10. So you just need to know how to read that notation. That's n, and probability of success is that. So part A says find the standard deviation of x. That's the clear instruction that we need to complete. It is the standard deviation. So that will just very clearly tell us what formula to use. So that standard deviation is equal to n times p multiplied by 1 minus p, or the probability of failure. We can then go ahead and substitute everything that we know in. So that's 4 times 9 on 10 times 1 minus p, or 1 minus 9 on 10 will be 1 on 10. Now, there's many ways to be able to work this out. You can complete it in whichever way you find easiest. I'll just say 4 times 9 is 36 on, and then 10 times 10 is 100. And we'll do the square root of that. That will give me 6 on 10, which simplifies down to 3 on 5 as my standard deviation. For the examiners, 59% of students got this correct. It's only 1 mark, so that goes straight to the answer, and they have noted that it is the 3 on 5. So it looks like you do need to simplify your fraction here, unlike that first question there. The one thing that they noted for this question is that they are specifically looking for the standard deviation. We are not looking for the variance. So it seems like a lot of students found the variance instead, which is just this part inside. They want the standard deviation, which is the whole thing there. Okay, so part B, find the probability that x is less than 2. So what we're trying to say here is that we want to have either 0 or 1 successes. So we want to make sure that we have less than 2 successes. So the first thing that I would do is write that information out. So what's the probability that we either get 0 successes or we get 1 success? Now, of course, if we had a CAS calculator, this would be so wonderful to complete, but unfortunately we do need to do this all by hand now. So we're going to write out our binomial formula. So that will be n, so the number of trials that I have, that's 4, and out of those 4 trials, I want 0 successes. I know that some students also write it like this. It's the exact same notation, I just tend to write 4, choose 0. Then we have the probability of success, which they also told us it's 9 on 10, to the number of successes 0, and the probability of failure to the number of failures. I know at this point it's really tempting to go into decimals, and you can possibly do it through decimals, but I think it'll be a lot easier if you stick to fractions, because later on it'll be easy to multiply those numbers. But try it either way. Now for the second one, out of the 4 trials, I want 1 success. I want 1 success here, and I want 3 failures over here. Okay, now 2 really important formulas you need to know at this point. So if we have n choose anything with 0, then that's simply going to be 1, and n choose 1 is going to be n. So just make sure that you know these 2 formulas so that we can substitute them in. So for the first one, we've got 4 choose 0, that's just going to be 1. And then anything to the power of 0 is 1, so we're left with 1/10 to the power of 4. 1 on 10 to the power of 4 plus, and then 4 choose 1, as we said, n choose 1 is always n, so that's going to be 4 times 9 on 10 times 1 on 10 to the power of 3. Again, multiple ways of being able to work this out. What I like to do is try to reduce the large numbers. So over here I can see that there is a common term between these two, or common factor rather, between these 2 terms over here. So I'm going to pull out the common factor of 1 on 10 to the power of 3, which exists in both of them. So we'll start off with 1 on 10 to the power of 3. And once I do that, so I've taken 3 out, what's left over will be 1. So that will be 1 on 10 plus, and then over here, I've taken all 3 out. So this whole thing is gone. So here is 1 left, and here there is none left. This will make it easier to be able to count the numbers. So you can expand this straight away. I'm just going to leave it to the power of 3 for now. That's 1/10 plus, and then 4 times 9 is 36 on 10. So that'll then be 1 on 10 to the power of 3 multiplied by, and then 1 plus 36 is 37 on 10. And now we can multiply this all out. So 10 to the power of 3 will be 1,000, 3 zeros, and then times 1 more 0 will be 10,000. So that'll be our solution for this question. Examiners. So first of all, 39% of students were able to get full marks for this. The marks lay, we've got the first one over here, which is writing out that binomial expansion. And then we've got the mark at the end, but they did note that it can come in any form. So whether you write it in decimals or fractions or some sort of other variation, as long as you get to that particular answer, they will accept it. You do need to simplify it though. So this is not an acceptable answer. For example, you could have even written something like 37 to 10 to the 4. Okay, that's the end of question 4. On to question 5, some wonderful transformations coming up. Question 5. The function as follows models the population of a town after 2 years. So before we even start with our parts, I just want to highlight key points in this question. So the first thing are the variables that we're using. So instead of x and y, it's just very important to note that we're using h and t. I'll also highlight the domain in case we need that later on. And then of course the actual function itself, which this is a hyperbola. So it looks something like that. I might draw a little sketch just so I know exactly what it looks like. Also, what's really important is to understand the units. So this is after t years. So t is in the units of years. Okay, we can now go ahead and start reading the question. So it says, use the model h of t to predict the population of the town after 4 years. Pretty straightforward. T will simply equal to 4. And we are predicting the population, so that means we're looking for h. Simple substitution. H of 4 is equal to, that's 3,000 divided by 5, which is 600. So after 4 years, you'll have a population of 600. 95% of students got this question right, which is great. It should just be a simple substitution for you. Okay, part B. A new function h1 models a population where h1 of 0 is equal to h0, but also h1 decreases at half the rate of h at any point in time. Very interesting wording. So first of all, h1 of 0 is equal to h0, so the starting point of both of these graphs is the same, but the rate is going to be decreasing at half of that of h at any point of time. And then it tells us to state a sequence of two transformations that maps h to h1. Now, very interestingly, before we even start this question, 2% of students were able to get full marks for this question. It's very interesting. Now, it is not an easy question to kind of visualize because there's a little bit interesting going on in terms of making sure that the starting point is the same, but also that the rate is decreasing at half. You can kind of try to think your way through it. I would always suggest that you try to sketch the graph and make sure that that is correct according to the transformations. But there is also a mathematical way to do it where it takes off that mental load and you will always get to the right answer. I'll just start off with the quick way of doing it and then I'll explain it through the mathematical reasoning. So in terms of what's happening, I'm just going to draw up our graph. So this is just my thought process here. That's why I'm drawing it in blue. This is a graph. We said that it's a hyperbola. It starts at 3,000 and it's had a shift of 1 to the left. So that's why it crosses the y-axis and it's going to look something like that. And then basically what's happening is that we've got this new graph, h of 1, which I'll draw in pink, and we are decreasing at half of the rate of it. However, it has to start at the same value. So it has to start at that 3,000, but then we want that to be half of what we would with the blue. So basically, whatever this blue value is, we would have half of that value at any point. Now, that doesn't really make sense in terms of what I've drawn. Why is it higher? So if we think about it, if I'm halving every single one of my y values, it should actually look something like this. The problem is that I will also be halving that initial point. So I'll be halving that 3,000 to become 1,500. But I don't want it to be 1,500. I want it to start at 3,000. So instead, after I've halved all of my y values, what I have to do is I then need to shift that graph upwards so that it does start at that 3,000. So that's essentially what's happened. First, I'm going to halve all of my y values, and then I'm going to shift the graph upwards so that it starts at the exact same point. So our two transformations would be, we will have a dilation of factor 1/2 from, and because we're moving in a vertical direction, it's like we're starting at the t-axis and then we're moving away from it. You can also say parallel to the h-axis, either way. And then we will have a translation of 1,500 units. The formal way is to say in the positive direction of the h-axis, but it's actually okay and accepted to just say up. That's fine too. Now, an alternative is to actually say that you will translate it first, 3,000. So you start at 6,000 and then you divide everything by 2. That is also a valid response. So the examiners also accepted that. But I just feel like this is what kind of makes the most sense for me in my head. All right, so that's your answer there. That will earn you the 2 marks. However, obviously, a lot of students were unable to get to that particular answer. So let's talk about, if you're not too sure, if you weren't able to sketch it, if you're not able to visualize it, how can you do this mathematically so that it takes that mental load off and you can make sure that you've done it correctly? Well, I'm going to follow the exact wording of what it says. H1 decreases at half the rate. What is the rate? That is H dash. It is the derivative. So we want half of the derivative of t. That is half the rate. So that's the first thing that we know. So let's go ahead and actually do that. I'm going to multiply the derivative of h of t by a half. Now, how do I find that derivative? Remember, the graph is 3,000 on t plus 1. This, if I take it to the top, becomes to the power of -1. So the way that you differentiate that is you take 1 away from the power and you also multiply by that initial power. So that'll be times negative, and there'll be 3,000. And then if we take 1 away from that power, it'll be to the power of 2. So crossing that out, that will become 1,500 on t plus 1 squared. That's half of the rate. However, I don't want the derivative. I don't want the rate. I want the original function. So what I'm now going to do to get to that original function of h1 of t, I'm going to anti-differentiate that because that's the rate. So to anti-differentiate, we're going to add 1 to the power and divide by the new power. Now, keeping in mind, the new power is -1 because at the moment it's -2, even though it's at the bottom. If you take it to the top, it's -2. New power will be -1. And then, so I'm just kind of trying to do it all in my head here. So add 1 to the power becomes -1, and you have to also multiply, or rather divide, by that new power. So there's a -1 there, and if I'm dividing by -1, the negatives will cancel out. If that's a little bit too much to do, just write it all out by hand, you'll get the exact same answer. So that's why it's a positive there. But of course, whenever we integrate, we also need a plus c. So where do we get this c from? We need to substitute in a point, and that's where this second part comes in, that h1 of 0 is equal to h0. That means the starting point needs to be the same. So the original graph, when t is 0, y is 3, or rather h is 3000. So all we have to do now is substitute that point into the graph. So that'll be 3000 is equal to 1500, 0 plus 1 plus c. So 3000 is equal to 1500 plus c. Therefore, c will equal to 1500. That means h1 of t is equal to 1500 t plus 1 plus 1500. And here you can see the transformations, dilation by a half, and then a translation of 1500 upwards. So if that helps you to do it, you can actually, well, it's actually all of this, you can do it mathematically. So it removes, or it releases the mental load of needing to actually try to draw the graph and am I correct or am I not? That's the hard thing with transformations. There's a lot of uncertainty around it. So if that's the case, I would suggest just follow the wording and complete it mathematically. It might take a minute longer, but it guarantees you the mark. And I'm sure there would be a lot of students that would have benefited from doing it in this way. Okay, so that's part B. Now let's move into part C. We're moving into population proportions and a bit more probability-based ideas. So it says to us, in the town, there's 100 people who were randomly selected and 60 of those people were unhappy with the roads. So we are talking about, like our variable would be about being unhappy with the roads. Our population proportion is what I can get from this. So that's 60 of 100, simplified down to 6 on 10, or 3 on 5. So the question says to us, determine an approximate 95% confidence interval for the proportion of people in a town who are unhappy with the roads. Use z equals 2 for this confidence interval. This is just your basic confidence intervals formula. So that'll be p hat minus z, p hat 1 minus p hat on n, and then p hat plus z, p hat 1 minus p hat on n. And now it's just a basic substitution and working with a bunch of fractions. So I will do that. 3/5. Z, as they told us, is 2. And n is going to be 100. That's 100 people in the town. Okay. Now it's up to you in terms of how you want to work this out from here. So we can kind of do a little bit of work in our head. 3/5 times 2/5 is going to be 6 on 25. And then when that's on 100, what you do is you multiply the two denominators. So that'll be 6 on 2500. Actually, there should be a square root there. So that'll be 6 on 2500. And then the same for the other side. Okay, so that's 3/5 minus. Now we've got to deal with the surd. So we really can't do much with the 6. However, for the 2500, if you think about it, that's 25 times 100. And so the square root of 25 is 5, and the square root of 100 is 10. So that should be on 50. And we can go ahead and simplify that. So that'll just be 25 at the bottom. And you have your answer. Now you can go ahead and put this all on one fraction if you like for both of the sides. You might have used decimals from the beginning. That's completely fine. So the examiners noted that it didn't matter how you actually got to the answer or what the answer looked like, as long as it was the equivalent to that. So examiners report, we've got 44% of students were able to get full marks for this question. Where those marks came from, we've got the first one setting up the actual formula, substituting in the numbers correctly, and then the last one being the actual confidence interval itself. And they did note that it didn't matter what form that was in, that's completely fine. They also did say if you actually use square brackets, you also got the mark. So that's good to know as a backup, but in general, we use circle brackets to indicate the interval. Okay, our final part says, a new sample of n people results in the same sample proportion. Find the smallest value of n to achieve a standard deviation of root 2 on 50 for the sample proportion. Okay, highlighting key parts. We've got a sample of n, so now we don't know what our n value is anymore, and it results in the same sample proportion, which means the sample proportion we're going to be using is what we had before, 3/5. Instructions. Find the smallest value of n to achieve a standard deviation of root 2 on 50 for the sample proportion. So the standard deviation is going to be your key here. We do have a formula, and it is in your formula sheet as well, in case you're not too sure. So that's going to be equal to P 1 minus P on n. So substituting in the values that we've got, that'll be 3/5 times 2/5 on n, and that is going to be equal to the standard deviation, which is root 2 on 50. From here, it's just really a bunch of algebra work. So the first thing I'm going to do is square both sides to get rid of the square root, and I'm going to simplify those fractions in there. So 3 times 2 is 6, 25, and remember, when there's a denominator or a fraction divided by a denominator, we just multiply it through, and then that will be 2. So I'm squaring that side as well, remember, and then 50 squared will be 2500. Okay, we want to get n by itself, so I might just go ahead and cross multiply. So we'll need to do 2500 times 6, or just think of it as 25 times 6, so it'll be 150. So that will be 150, add the 2 zeros, and then this will be 50n. And then I can go ahead and start. I'll get rid of the 0 first, then I'll have 1500 divided by 5. Well, the 15 and the 5 can go. That will be a 3. So what we will be left with is 300. Now, maybe it's not necessary to do all of this, but this is just how I work out larger numbers in my head. You might just look at it and know the answer straight away. That's great for you. But if you are uncertain, especially under that exam pressure, you can go through and just divide just like that. So n will be equal to 300. Now, examiner's report, we have for this one, 33% of students were able to get this answer correct. It's really just a 1-mark question. So that's over here. N is equal to 300. You either get it or you don't. Okay, moving on to question 6, we've got a log question here. Solve 2 log base 3 x minus 4 plus log base 3x equals 2 for x. So on face value, this question looks super easy. It's basically just solving a log question, but there's a little bit more to it that I think a lot of students missed. So just off the bat for this one, only 9% of students were able to get all 4 marks, and the average was actually 1.5 marks. So we're really seeing between those 1 to 2 marks that a lot of students were able to get, and they weren't really able to progress much further than that. Now, before I even start this question, I'm going to ask myself the question, for what values does this function of x exist? So they will usually give you a domain. In this case, they don't, which means they're leaving it up to you to work out what values of x are actually valid, because not all values are valid. What I can see here is a question that has 2 functions being added together. So I'm thinking of my addition of ordinates, and I'm thinking that the domain of the addition of ordinates is equal to the intersection of the individual functions. So the domain is going to be whatever works for both of them together. Now, what we know is for a log function, so we have log x minus m, the domain for this is going to be that x needs to be greater than m, because this inside part always needs to be a positive value. So considering that, what I can see is that for this function, for the first function, x needs to be greater than 4. And for the second function, it's x needs to be greater than 0. What's common between them is going to be x is greater than 4. If you're not really sure on how to work out what's common between them, I usually draw a number line. So I'll put in the domain of both of them in there. So x greater than 4 looks like this. X greater than 0 looks like this. What do they have in common? It's from here onwards. So I'll say where x is greater than 4. And this is really, really important to get those solutions in. Okay, now that we've established all of this, we can go ahead and start working out our question. So again, on face value, this seems pretty straightforward, but it is going to be a little bit more involved than a regular log question. So to start off with, I can see that there's a number here. I'm going to take that out. So log 3, and then I'm just going to write it in a bracket just to make it very clear that it's not the log being squared, but it's that inside function that's being squared. Plus log 3x is equal to 2. Now, because the bases are the same and the two logs are being added together, I can multiply the inside values. So that'll be x minus 4 squared times x is equal to 2. And now I can use a rule. That's where we take the 3 over as the base. So that will be equal to 3 to the power of 2 is equal to, and I'm just going to go ahead and start expanding this, because I'm going to need to expand it in a sec anyway. So remember, that's our a squared plus 2ab plus b squared rule. Now finally, I'm just going to do a full expansion. And I'm going to take everything over to one side. And you can see, unluckily, we're left with a cubic. Very annoying, because you can't easily factorize a cubic. Come in long division. Okay, so this is a whole process in itself. So the first step of long division is that we need to find a factor for this. We need to go ahead and test our numbers, 1, 2, 3, and so on. You usually test the numbers plus minus that are the factors of the last number. So really, I would only test 1, 2, 3, and 9, but I really hope we don't get to that point. So let's start off with x equals to 1. If I substitute 1 into all of the x's, I'll have 1 cubed minus 8 plus 16 minus 9, which does in fact equal 0. And thankfully that's the case, because I really didn't want to spend my time substituting a whole bunch of numbers in. So that means x equals 1 is a solution, and that means that the factor is actually x minus 1. So I can go ahead and start my long division straight away. So x minus 1 is a factor that I know of. Okay, and I can go ahead and start my long division now. I'm just going to use a different color just for a little bit of contrast. So we're thinking about x goes into x cubed, x squared times, and then I can multiply that out. So x squared times x is x cubed, x squared times negative 1 is going to be negative x squared. Subtract the 2, you should get 0 for this value, and then negative 8x squared minus minus, so plus x squared, will be negative 7x. Bring down the next term, and we do it again. X into negative 7x squared is negative 7x. Multiply that out, that will be plus 7x for this term. Subtract the 2, that should be 0. 16 minus 7 is going to be 9. So that's plus 9x, bring the last term down. And so then we'll end up with plus 9. 9 times x is x, 9 times negative 1 is 9, negative 9, and that ends up with a lovely 0. So there we go, that's our long division done, which means that our final two factors that we can get with x minus 1 and x squared minus 7x plus 9. Now just when we thought that we're onto the easy path, being able to factorize it, if you have a look at this quadratic, that's not something you can factorize in your head. There are no two numbers multiply to give 9 and add to give 7, unfortunately. So x equals 1 is a solution. We already know that. We now need to solve this. So you can either complete the square and solve for it that way, or you can use the quadratic formula. Just because there's odd numbers and negatives, I don't want to deal with it. I'm just going to go straight into using the quadratic formula. So just to note, the quadratic formula will have the coefficients a equals 1, b equals negative 7, and c is equal to 9. And that's going to take me straight to my solutions. So quadratic formula, negative b, so minus minus is a positive, plus minus b squared, so that's 7 squared, minus 4ac on 2a. So that'll just be 2 times 1, which is 2. Simplifying that out, we'll get 49 minus, and then 4 times 9 is 36. So that's going to be root 13 all on 2. And that's basically your solution. So our three solutions lined up in order will have 7 minus root 13 on 2 and 7 plus root 13 on 2. Going back to now our initial part of the question, we clearly set a domain that x needs to be greater than 4, so x minus 1 is not going to work. Our question is, are these in the valid domain? Some of you might be able to look at that and know straight away. For those that don't, I'll just show you a quick way to work that out, and that's to estimate what that root 13 is. Now, root 13 is going to lie somewhere between root 9 and root 16. So root 9 is 3 and root 16 is 4. So that is going to be somewhere between 3 and 4. Now, if I take the smaller number, which is 3, so that will give me the largest possible answer, 7 minus 3 on 2. 7 minus 3 is 4. 4 divided by 2 is 2. So regardless, even when I take the smallest of the possibilities of root 13, it is still not going to be part of the valid domain. So that means that my final answer will be x is equal to 7 plus root 13 on 2. And make sure you make that very clear on your exam. So I would probably write something like, that is the solutions. Look here, examiners. All right, what a big question. Something that seemingly should be so easy, solving a bunch of logs. They've integrated a whole bunch of things, including long division, again from your year 11. That is going to be quite tricky. So what do the examiners have to say to this? So the first mark comes from coming up with this quadratic factor here, the x minus 4 all squared. They have noted that it's not x squared minus 16, which absolutely kills me every time I see that. Please, this does not equal x squared minus 16. There is an actual method to doing that. If you were to expand it, you're a squared minus 2ab plus b squared. So please don't do that. Make sure that we are sticking to correctly expanding those numbers. Okay, so that's fine. That's our first mark. Our second mark comes specifically from, it says factorize to get correct linear, x equals 1, and any quadratic factor. So the way that I'm reading that is that you need to get that x minus 1, but you also need to get any quadratic factor. So even if you kind of did it wrong and you stated it as a quadratic, it sounds like you might still get the mark there. Obviously try to not do it wrong, but as long as you get to that point, which means you've shown some sort of attempt to being able to factorize it and getting a solution, then you should be able to get a second mark. Okay, that was our second mark. Now for our third mark, it's an answer mark, and that is to get all of these three solutions. So you need to get all three, and then our final mark, of course, was to state that that is the solution itself. There is no justification that's needed. So all of this working out, you don't need to write it. Even if you just wanted to take a guess that this is the correct solution, you'd still get that answer mark there. So a big question for something that seems so small, but it is worth 4 marks, which is quite a lot as well. Okay, moving on to our last couple of questions now. We've got question 7, where we're going to be using some circular functions. Question 7 says, part of the graph f of x equals x sine x is shown below, and part A says use the trapezium rule with a step size of pi and 3 to determine an approximation of the total area between the graph of f of x, the x-axis, over the interval of 0 to pi. So in terms of highlighting key information, I'll just start off with the name of the function, which is f, the domain, and also the function itself, which is x sine x. And the instructions, what do we have to do? Use the trapezium rule. We've got a step size of pi and 3, and we want to go between 0 and pi. Now, you don't have to do this, but I like to draw in my trapeziums just to make sure that I've got everything in correctly. So there's my first one, first step of pi and 3. There's the second one, and there's the third one. So the way that I remember the trapezium rule is by the actual area formula itself, which is a plus bh, a plus b being the heights of the trapezium. And so in terms of the heights, what I want is I want to find the y values of each of these, and the way I do it is by substituting in the x value into the function itself. But what we want to remember is that the inside parts here belong to 2 trapeziums. So that belongs to that trapezium and that one. So I'll need to multiply it by 2. That also belongs to 2 trapeziums, so we'll multiply it by 2. Whereas the outside values only belong to 1 trapezium, so we will not need to multiply by 2. So given that, the way that this rule will work, we've got f of 0, so that's to find the height of that initial part over here of the trapezium, plus, and then we'll have 2 lots of f of pi and 3 because it belongs to 2 trapeziums, 2 lots of f of 2 pi and 3, and then 1 lot of f of pi. And then we multiply all of that by the height of the trapezium itself. Next thing we're going to do is start evaluating. So f of 0, f of pi, that's both saying sine of 0, sine of pi, which are both going to be 0, so I don't need to worry about those terms. And then I'm going to evaluate those inside terms there. So that'll be 2 f of 3 and 2 f of 2 pi and 3. And I'm just going to do it on the side to try and keep it as neat as possible. So that'll be 2 times x, which is pi on 3, times sine of pi on 3, which will be root 3 on 2. And then same with this one, 2 times 2 pi on 3 times sine 2 pi on 3. So the exact value will stay root 3 on 2. It's in quadrant 2, which is positive, so it's the same thing, root 3 on 2. Now we can go ahead and try and simplify this as much as we can. So the 2's will go. That will leave me with root 3 pi on 3. And here the 2's will go, and that will leave me with 2 root 3 pi on 3. Okay, so now we can continue on with our area. So that'll be a half. We'll have root 3 pi on 3 plus 2 root 3 pi on 3 multiplied by pi on 3. I'm going to go ahead and multiply the half and the pi on 3. So that will give me pi on 6. And then on the inside, that will be 3 root 3 pi on 3. The 3 and 3 should cancel out. And so what we'll be left with is root 3 pi squared on 6 units squared as my final answer. So in terms of the examiner's report, we'll have 30% of students that were able to get full marks for this question. The marks lay in. So the first part was setting up the trapezium rule itself. The second part was evaluating the values or finding the heights. And then the third part was providing an answer. And they did note that the answer was okay to be unsimplified. So it didn't really matter what form you gave it in. As long as it's the correct answer, they were able to give you the full marks for that. Part B says find f dash of x. So just to write it out again, f of x is equal to x sine x. We will need to use the product rule once again. Feel free to do it in your head. I just want to release the mental load, so I'll just write it all down. And then we will multiply across. So f dash of x will equal x cos x plus sine x. That's part B, and 84% of students were able to get that correct. One thing the examiners noted, that the f dash of x had to either be there, or if you wrote y, you would not get the mark. So you just have to be really careful with that notation. So you should write f dash of x equals this, not y equals. Okay, on to the next part now. So part 2 says determine the range of f dash of x over the interval pi on 2 to 2 pi on 3. The key word here is determine the range. And when I think of the range, I always think of sketching the graph, because it's not always as simple as substituting in the endpoints, and that'll give you the range. If there's some sort of turning point, you can see that the range is not just going to be the endpoints here. It can be the turning point itself. So it's really important to sketch the graph so we can see what it looks like. However, I don't know about you, but personally, I don't know what the graph of x cos x plus sine x looks like. And I want to alleviate my mental load. I don't want to have to try and think through it. So this is where reading time is so important. If you have read ahead during reading time, you'll notice that part C actually says on the set of axes below, sketch the graph of y equals f dash of x. So this is one of those times where I'm going to actually do the next part first. I'm going to do part C, and then I'm going to use part C to help me with this part here. Now, others might have a different way to do it. I'm sure there's a reason why they've asked us for the range before sketching the graph itself, but I think this is the way that I would approach it if I'm under that exam pressure and I just want to get it done as quickly as I can. So let's go ahead and do that. Let's focus on part C, and then we're going to come back to work out the range. Now in part C, it says on the set of axes below, sketch the graph of y equals f dash of x on the domain negative pi to pi inclusive, labeling the endpoints with coordinates. And it's very important to do that because that means that there's a mark that is involved there. It says you can use the fact that y equals f dash of x has a local minimum at this coordinate and a local maximum at this coordinate. So that's really important information to include as well. So to sketch our gradient graph, the x-axis stays the same, but the vertical axis turns into our gradient. So that means any coordinate that I put in, that second coordinate, that second value is actually going to be the gradient at that point. So I'll always start off with the stationary points because the gradient of a stationary point is 0. So I can see the stationary points at negative 2, 0, and at 2. So those points will go in first. Next thing that I can do is look at the endpoints because it specifically told me about labeling the endpoints, which means I need to have a very specific gradient for those. So the endpoints are happening at negative pi and pi, as they told us. So I'm going to go ahead and sub that into my gradient equation. So if we do f dash of pi, that'll be pi cos pi plus sine pi. Now sine pi is just 0, cos pi is negative 1, so then that will end up being negative pi. So if I go ahead and put that on the graph, that'll be about here. Now the one thing is, because this is an endpoint on the original graph, the actual gradient at that point does not exist. So it would be negative pi if it was continuous. However, because it is not continuous at that point, we will draw it with an open circle. Same thing goes for negative pi. We'll substitute that in. So that'll be negative pi times cos of negative pi plus sine of negative pi. Now sine of negative pi remains 0. Cos of negative pi, that's the same as cos of pi, so that'll be -1. So now it's negative pi times -1, which will be positive pi. So that'll be somewhere up here. All right, we're almost there with our points. We're just going to go ahead and put in the local minimum and maximum that they've provided us with. So the local minimum is at -1.1 and 1.4. So that should be something around here. And then 1.1 and 1.4, somewhere around there. And now what we're going to do, to the best of our ability, is go ahead and connect the dots. There we go. That looks like a pretty good graph there. Okay, so just before we go on and have a look at what the examiners have to say, I'll always reread the question just to make sure I've done it correctly. So first of all, I've extended across the correct domain, labeled the endpoints. I actually have not done that. So let's go ahead and do that. That'll be pi and negative pi. And this one is pi and actually negative pi and pi. So that part's done. And I have included these. It doesn't say anything about labeling, so I don't really need to label at that point. All right, let's have a look at what the examiners have to say. So first of all, 15% of students were able to get all 3 marks for this question. The marks lay in, first of all, the shape. It needed to have a negative cubic shape that looked like this, and it needed to clearly extend past -3 and 3. So you really need it to be over that negative pi to pi domain. They also clearly say it shouldn't be bumpy. So if you drew your graph looking something like this, it's not going to get the mark. You saw when I drew my graph, I drew it in 2 parts looking something like this, just to try and make it as smooth as possible. Your second mark lay in the key points. So that includes your local and maxima and minima. It had to pass through them, but you didn't need to label them, so that's fine. It says it needs to cross the x-axis under the turning point, so that's these points here, and it had to pass through 0, 0. So that's all of your key points. The final mark is the endpoints with the correct coordinates and the correct positions. So that's where your 3 marks lie, and as mentioned, only 15% of students were able to get all of those marks there. Okay, so now that we've sketched the graph, we can actually go back to part 2 to being able to determine the range over this particular interval. So I'm just going to go in with a different color just so that we can clearly see what's happening in terms of what that domain is, pi on 2 to 2 pi on 3. So I'm going to just try and find those values. Now pi on 2 will be half of pi, so that's just going to be something around there. And then 2 pi on 3, if I were to split this pi up into thirds, so we might have one there and one there, this one's probably your 2 pi on 3. And that's pi on 2. Regardless of where the point actually lies, what we can see is that it does have that particular shape where it's going downwards. There's no turning points involved. So the endpoints of this particular graph is going to coincide with the range itself. And that's great for us. So we can just sub in the x values and then it'll give us the y values. The only difference is that our lower x value will give our higher range and our higher x value will give our lower coordinate of the range. Okay, so let's go ahead and substitute in all of our values now. So we'll find f dash of pi on 2. That'll be pi on 2 cos pi on 2 plus sine pi on 2. Now we know that cos pi on 2 is 0, so that term is going to be 0, and sine pi on 2 is 1. And then we have f dash of 2 pi on 3. So that'll be 2 pi on 3 cos 2 pi on 3 plus sine 2 pi on 3. Now cos 2 pi on 3 is going to be a half, but because it's in the second quadrant, it'll be negative. So we'll have 2 pi on 3 times negative a half. The 2's will cancel, so we'll end up with negative pi on 3 plus, and then sine 2 pi on 3 is root 3 on 2 in the second quadrant, so it'll stay positive. So that's root 3 on 2. So that should be our value for that. That means our range is going to be from our smaller value, and now I'm just going to change the order so that the negative ends up in the middle, to 1. So make sure that you have the smaller value first and the larger value second. So for this question, 20% of students were able to get this one right, and in terms of the examiners, they've just made note that you needed to make sure that it is in the correct order. So some students would have just subbed in the endpoints and wrote 1 and then their second number there, but you need to make sure that the lower value is first and the higher value is second. So if you swap those, that was incorrect. Okay, final part for this question here. It says, hence verify that f of x has a stationary point between pi on 2 and 2 pi on 3. I just want to point out the most important part of this question, which is hence. Now, hence means you must use the previous part. You'll see that a lot of questions usually say hence or otherwise. So they're suggesting to you to use the previous part, and it's probably going to help you. But if you can't, that's okay to do it another way. In this case, that is not the case. You must use the previous part that you found. So they want us to use the fact that the range is root 3 on 2 minus pi on 3 and 1. And so we'll have a think about how that is involved. Next, it also says verify that it has a stationary point. So it is telling us it definitely has a stationary point. We just have to prove it. Now, in terms of the word stationary point, the immediate thing that I always think of is that the gradient is 0. We're just going to talk about what the range is for this particular graph. Now, we always think of the x is the domain and the y is the range. However, in this case, this is the range of the gradient graph, which means these are all of the possible values that the gradient can take. So the gradient are these values here. Now, in terms of these values, what you might notice is that this value here is actually a negative value. Now, if you're not certain about that, if you look at the graph, you'll see that it actually lies below the graph itself. So once again, that shows us that that is a negative value. However, 1 is a positive value. So if we have a number line and we have our 0, we have all the negatives on this side, so we'll have root 3 on 2 minus pi on 3 here, we have 1 over here, and we can see that the range goes from there to there. What this must mean is that the range at some point has to cross the value of 0 since this graph is continuous. And we know that if we have a gradient value of 0, it means that there must be a stationary point. And that would be your answer to this. So as the value of 0 is included within the range of that, then there must be a stationary point. Now you can just write that out in words. So as the range includes the value of 0 as a gradient value, if you want to just kind of drive that home, there must be a stationary point. Okay, so I would state the range first of all, and then I would just say that the interval needs to include the value of 0. Because it includes the value of 0, which is the gradient, there has to be a stationary point within this domain here. And that's basically your answer for this question. Now for the examiners, only 12% of students were able to get this question. This one's quite tricky because it's kind of like an understanding question. So some students might have known what the answer is but couldn't quite express it. Others might just not have been able to understand exactly what it's trying to say. The examiners said that you have to use your part 2. That's what we spoke about in terms of that hence word. You need to use part 2, and that's why I immediately wrote the range. So I've used what I've previously got. You can write it in terms of words, so you can state either the inequalities or you can state that the range includes 0, so the gradient must be 0 in the interval. That's pretty much it for that particular part. I will say that VCAA, it is unusual for VCAA to include some sort of question like this that requires such a deep understanding, but as you can see, they have thrown it out there and it does really require you to think. Okay, that's the end of this question here. We will now move on to our final question, question 8. Okay, we've made it now to question 8. Let's give it a go. So it says, let the graph of g of x be equal to that function where k is a real number except for 0 and m is also a real number. Let the point b be the y-intercept of the graph of y equals g of x. So first thing I want to do is just a quick highlight, notation, g of x, the actual function itself, a little bit of information about the k and m. I mean, they're just real values, so it's up to you whether you want to highlight it or not. One really key point though is that the point P is the y-intercept of the graph. And when I think of the y-intercept, what I'm thinking is that we have some sort of x value and the y value being 0 there. So we're going to start with part A. It says find the coordinates of P. That's our instruction, find the coordinates of P in terms of K and M. So when we say in terms of K and M, we want K and M to be within that coordinate there. Okay, pretty straightforward. It's basically just trying to tell us find the y-intercept of this graph. The y-intercept, of course, we know is where x is equal to 0. So we're just going to find y is equal to 0 minus k plus m. That'll just be the third root of negative k plus m. And so as a coordinate, that's just 0, third plus m. So that's that first part there. 61% of students were able to get that question right, which was very good. And just be careful of your notation here. A lot of students wrote 3 times root negative k, and I'm sure that this is what they meant, but it's really important to write little 3, not the big 3. So just be careful with that. Okay, part B says find the gradient of g at p in terms of k. So gradient of g at p. So the first thing is we need to find the gradient of g, that's g dash of x, and then at p, because that's the y-intercept, that'll be g dash of 0. So step 1, step 2. Okay, so I'm just going to start off by differentiating the function. Just to make it a little bit easier for myself, I'm just going to write it with a fractional power. So we will take the power out the front, that'll be 1/3 x minus k, and subtract 1 from the power. Now because m is a constant, then that's going to go when I differentiate it. I'm just going to simplify it also by writing it like this, to the power of 2/3. So that's part 1, that's the gradient of the graph. Now we want to find it at p, which means we're just going to go ahead and substitute in 0. So that'll be g dash of 0, wherever I see x, I'm just going to put in 0, negative k, that. Now, if you want to leave it like that, that's completely fine, but I do recommend that you actually go ahead and simplify it. And the way that you can consider it is that because we are squaring it, we are squaring this negative k here. Whenever you square a negative number, it's always going to be positive. So that's just the same as saying 3k to the power of 2/3. But if you did leave it in that other form, that would be fine. I just prefer to get rid of negatives wherever it's possible. Okay, so 32% of students were able to get this correct. The place where you get the marks, first of all, you had to differentiate it correctly, and you also had to attempt at substituting in that 0. So as long as you substituted 0 into a correct derivative, you were able to get that first mark, and then the second mark there was to get that particular answer. However, they did accept it in any particular form, so even from beforehand, that's fine. It doesn't have to be fully simplified. Okay, part C says, given the graph of y equals gx passes through the origin, key information, express k in terms of n. That's our instruction. So k in terms of m means I need to write k equals something, 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 and the m is in the inside. Now, given that it passes through the origin, that means both x and y is going to be equal to 0. That means that I'm going to go back to my original graph, g of x, and I'm going to substitute in 0 into both x and y, and then I can rearrange the function to get k by itself. So that will be something like 0 is equal to the cubed root of 0 minus k plus m on the outside, and now we can rearrange that. So that'll be root 3 negative k plus m equal to 0. And remember, I want to get that k by itself, so I'm just going to take everything else over. So that'll be negative k is equal to negative m. And then the way to take that cubed root over is to multiply by the opposite or the reciprocal root. So that there is 1/3. So I will multiply both sides. Well, really, I will raise it to the third root on both sides. That's the proper mathematical language. So negative k is equal to negative m to the power of 3. And then we can divide both sides by -1. Now that negative, whether it's on the inside or the outside, doesn't really matter with the cube. K will be equal to m cubed, as the negatives will cancel out on both sides. All right, so that's the relationship between k and m. In terms of the examiners, 47% of students were able to get this question right. And now let's move on to our very last part. It says, let the point Q be a different point from the point P, such that the gradient of G at points P and Q are equal. So it's very key information there. What we know is that the gradients at those 2 points are the same. Now, what I'm just going to highlight also as key information is the gradient. And we have previously found the gradient of the graph. We did that in part B. So the gradient in general is 1 on 3 x minus k to the power of 2/3. That's all on the denominator. So I've just written that there just so I can keep that in mind. And I know specifically that at the point P, it's when it's 0. There should be a dash there. It's when it's 0. Okay, it says, given that the graph of y equals gx passes through the origin, so more key information, I'm just going to connect that So just in terms of my thought process, that connects to this point here. So if it passes through the origin, that means this statement here holds true, that k is equal to m cubed. Can you see how as I'm going through the question, I'm relating it back to the previous part? So that's generally what VCAA do, particularly with those later questions. It's all about what information can you get from the previous parts of the question and apply it to this over here. Okay, so it passed through origin. It asks us to find the coordinates of Q in terms of M. So we only want M. Actually, that's an instruction, so that should be in green. Find the coordinates of Q in terms of M. Okay, so now that we've got this kind of information, let's go ahead and try and apply it as best as we can. So again, following what the question has given us, it's told us that the gradients of P and Q are equal. Now, P is specifically at the point where x is equal to 0, so we can go back to that previous question. We can see that the gradient of P is this over here. So that's 1 on 3k 2/3. Q, we don't know what value that happens at in terms of x, so we can just write the gradient equation in general, and x will just be the coordinate at Q, which is exactly what I'm looking for in this question. 1 on 3 x minus k 2/3. Now the question specifically tells me that it wants it in terms of m, and the problem is I have it in terms of k right now. We don't want that. However, because it passes through the origin based on what we found in part C, we know that k is equal to m cubed. So let's get rid of those k's right off the bat and put m in so that I'm already on track. This will also help me in simplifying the questions, as you're going to be able to see in a sec. I'm just going to write that out properly. M cubed 2/3. All right, and look what that's now done. Very conveniently, 3 times 2/3, the 3's can cancel out. So I will end up with 1 on 3m squared is equal to 1 on 3x minus m cubed 2/3. There's a few things I can do here. First of all, if I multiply both sides by 3, that's going to cancel out with those denominators of a third. The next thing I can do is cross multiply so that I can get everything to the top and make my life a little bit easier. Okay, so what we're trying to do right now is we're trying to get this x by itself, because that x represents the x value at Q. So if I just want to be super clear, so this is x at the value of Q. We're trying to isolate that. First thing I'm going to do is try to get rid of that 2/3. So to do that, I'm just going to raise it to the reciprocal power. So that will be times 3 on 2. And as you can see, very nicely, those 2 will cancel out. I'll just continue on this side. So that'll be m cubed is equal to x minus m cubed as well, because the 2/3 and 3 on 2 will go. Now I'm going to take that m cubed over. So x will equal to m cubed plus m cubed. Therefore, x is equal to 2m cubed. That is the x coordinate of Q. Now all that's left to find is the y coordinate. To do that, I just need to sub that into our g value, our g function, g of x. So if we go right back to the beginning, so we'll have g of 2m cubed is equal to -3. Instead of writing x, I'm just going to write 2m cubed minus, now instead of writing k, which is the next part of the function, I'm going to write m cubed because that still holds true, and plus m at the end. Not too much I can do here other than 2m cubed minus m cubed is going to be just m cubed plus m. Now, keeping in mind, this is a third. So if we've got m cubed to the power of a third plus m, these will cancel out. So we'll end up with m plus m, which is equal to 2m. So that there is going to be the y value. So our final coordinate is 2m cubed and 2m. I'll just highlight that just for extra emphasis. That is our answer. Now for the examiners, 9% of students were able to get this question correct. Obviously, it's the last question of the exam. We do expect such a low number there. If you really think about it, this is a bunch of algebra, but it does require you to really break down the question to access what the question's asking you to do. And hopefully you can see the way that I've been able to highlight and just annotate as I go along, and then that helps me put all of that information through together. Now, in terms of where the marks lie, the first one marks in creating some sort of gradient equation here between P and Q. The second mark is finding that x is 2m cubed and an attempt at finding the y value. So there needs to be some sort of substitution in there. And then the third mark lies in actually finding that final coordinate. Now, I will say that this is not the only way to do it. You can actually also do it graphically, but that's going to take a whole other step to do. If you are interested in seeing it, again, please let me know and I'll create a separate video. But this is the way that I would have personally approached it. I definitely prefer to do it algebraically and just use the information I've already got rather than creating more of a mental load and trying to come up with an alternative route when I'm on the very last question of an exam. And that's the full walkthrough of the 2024 Methods Exam 1. I hope you found this video useful, not just to see the solutions, but also how to think through questions the way that the examiners intended. Remember, the examiner's comments are gold. They tell you exactly where students commonly go wrong and where you can pick up easy marks just by avoiding these traps. If you found this video useful, check out my other exam walkthrough videos or short concept videos, and also feel free to let me know in the comments below if there's any particular topic or question that you'd like me to cover. I'd love to hear from you. Thanks for watching, and I'll see you next exam.